Hello, everyone. First off, I would like to thank the QCon staff and organizers, especially Leandro, for inviting me here. Really a pleasure to be here today. This is the only slide that I have. Everything else is 100% demo-based. For full transparency, my demo wasn't working until about 2 hours ago, so if you could say a prayer for me to the demo gods, that would be fantastic. Okay, yeah, so my name is Bill Westlin. I am an engineer at Uber where I focus on infrastructure performance, specifically through the use of distributed tracing. Who here knows what distributed tracing is, just by show of hands? Okay, that's not too bad. Well, hopefully by the time you guys walk out today, everyone knows what distributed tracing is, and if you already know, maybe you've learned a couple new use cases. I want to start off with a story about how I found distributed tracing. So a couple years ago, I was working at EMC on distributed databases, and we were running a strongly consistent database primarily for financial purposes, which means that the failure modes needed to be extremely well documented. All of the edge cases needed to be known. It needed to be thoroughly tested. We were running with kind of a local quorum, kind of a virtual quorum between geographic sites. Distributed databases have a lot of tricky problems. Distributed locking, leader election. When we would load test this database, these nodes were emitting like tens of thousands of log lines a minute. We're running in our standard deployment with tens of nodes across the world. And sometimes these tests would run for potentially hours before there was a known failure. So that meant when we wanted to diagnose what actually happened, we were faced with this huge problem of reconstruction. We needed to somehow, from all of these disparate logs, piece together back what had actually happened. We were a small team of 4 people, and so the problem of log collection, parsing, seemed to be on an equivalent scale of building out this database in the first place. So I started to look for alternative solutions, and that's where I came across distributed tracing. And tracing really solves this problem with ease. And what I'm going to show you today is how much further you can push this very rich data set of tracing data. So I want to get started just by kind of introducing what distributed tracing is with a few examples, and then we're going to move into performance use cases and what you can really do with the richness of the tracing data set. First off, I just want to point everyone's attention to this blog post from Yuri. Yuri is the founder of Jaeger and one of the founders of Open Tracing. I got this demo running just by following this blog post, so if anyone wants to go home and take tracing for a ride, this is absolutely the place to start. Okay, so we're going to learn about what distributed tracing is through example. What we have here is this demo application called Hot Rod, and what you can do is choose to order coffee, desserts, chocolate, or flowers. Maybe in the near future you could do a self-driving car or a self-flying car. But for now, this is kind of a simplified analog of what our business does. So we're going to go ahead and order flowers, chocolate, desserts, coffee. Okay. This is pretty representative of what people see when they're testing their APIs. We see that there was some response, we get a latency measurement, and that is kind of it. There is this barrier for observability at the API level. This is the same problem that I was facing in a different way while building out my distributed database, this problem of reconstruction and introspection. So what we can do now is jump over to Jaeger, and we can see what actually happened as part of these traces. So we have get dispatch in the last hour. I think that this is right. Yeah, there we go. So from our demo application, all we could see is that this request succeeded. This was going to happen. But now with the tracing context, we can see really what happened in our microservice architecture. So looking through this trace, we can see that there is a dispatch event. It hits the front end for customers. It ends up at a MySQL database. Then we attempt to find the nearest driver. This seems to span out to a series of Redis calls. And then in parallel, we have calls to get route. So this is some kind of mapping type application. And eventually it results in a driver being dispatched to pick up a rider. So this is really just the first phase in what would be an actual trip flow for Uber. I spoke a little bit about how this is context. I want to show you how rich this data set is and what we can glean from not just the structure, but what is attached to each one of these spans. So we have logging event attached to the root here. And we can see that we got a customer, we found near drivers, then we kind of fanned out to each one of these drivers to decide what route would be the quickest. Finally, we found routes, we decided on a driver, and we dispatched this car. This right here is exactly what I was attempting to solve with my distributed database problem. And it's just laid out in order for me, attached to the exact trace that I care about. There's no notion of collecting all these logs, trying to parse through them, figuring out what went wrong and where. It is just easily displayed here for you. In fact, if we look down here, we can see this red exclamation point. So what happened here? We can actually see that there was a timeout on Redis. We can see what the driver's car ID was. The system was able to recover and continued. It looks like there are logs attached to this span too that show that there was a retry after the get driver error. So this just shows us very simply what the total chain of events were that lead to the successful endpoint that we saw here. A little bit about terminology that you may hear me use throughout this talk. The entirety of what we're viewing here is a trace. It's a distributed trace because it's jumping between many different services. Each one of these services does an amount of work and it emits what's called a span. So here on MySQL Select, we have a particular span. Okay. So this is a really interesting idea, this notion of tracing being used to bridge context divides. It can also be used to bridge organizational divides. Maybe you don't have the same standard of metrics collections in your databases as you do in your edge gateways. Tracing can serve as one unification for those entire paths. And then it is up to the individual instrumenters to decide whether they want to attach particular context or logs or errors, so on and so forth. This is really important in the context of testing systems. It is pretty well known in the Valley and I think in the industry at large that relying on white box metrics for alerting is not sufficient. White box metrics are extremely noisy. This is particularly true at Uber, where we have services that are serving multiple cities. These cities can have configuration changes that perhaps cause a single city to fail in a huge stream of requests. Those failures might not be obvious from white box metrics, right? So we need a way of reliably knowing if there is customer impact. And a lot of companies do this, just hit your APIs as if a customer would and alert based on those signals. So what we're viewing here is not a demo application. This is a redacted trace that we actually pulled from production. So I pulled this morning. This represents maybe eats, maybe bike, rush, freight, trip flow, anything like that. I do have context on this trace that I could determine, what hosts were running these services, what type of test this was, whether it succeeded or failed. But for now, we're just going to look at the pure structure of this trace. This is basically the full set of signal that you get from an external testing system. We can see each one of these spans either succeeded or failed. The test at some point decided to abort or it continued to completion. When we get an alert from this system, it is known that there is customer impact. That means that as a business, we are immediately beginning to lose large sums of money. But more importantly, our customers are impacted in a very meaningful way. Uber is used by millions and millions of people to get to the airport on time, to get to the hospital, to get to your job interview. When this system starts alerting, that means that people can't get where they need to go. So around the world, people spring out of bed, whatever time zone they're in, and they start firefighting this immediately. And it's expected that these are handled in a small, single-digit number of minutes, basically, to resolve this. So from a single known failure at a span, it used to be the case that these on-call engineers needed to deduce what the root cause of the failure was. This is the kind of context divide that I'm talking about. We have an external signal that ends at our API, and we have metrics internally that we can use to try and figure out what the root cause might be. Tracing makes this whole process far, far simpler for us. So this is the same trace, but now with internal context revealed. This is all still redacted, but I just want to give you a sense of how complex the underlying system actually is. Okay, so this is all still just to serve one single test. This is essentially the equivalent of what we see here. Uber is running somewhere between 5,000 and 10,000 microservices. I'm not just saying that for legal reasons. I actually don't know. One of the core tenets is to let builders build. And that means that any engineer is able to RFC a new product, spin up a new microservice, make whatever change that they want to their service, with, of course, like buy-in from your peers and a bit of management approval, but you are pretty much enabled and empowered to do what needs to get done. The result is that you can build a business very quickly, but a single request looks something like this. And for outage prevention, this can really be a nightmare. Tracing solves this problem for us fantastically. So we have this sort of external signal that alerts with high confidence when there is customer impact. Now we can use tracing to bridge the gap into what is actually happening inside the data center, what particular systems are truly failing. If we aggregate these successful traces, we can build a representative model of what success looks like. We can do this for production data against our testing data and understand where our test coverage is to try and enhance tests and make them more complete. Here what we can do is look at the differences between failures and success and decide, based on error models, false positive rates, what actually was the failure here. So I can't show you the internal tool for that right now. I'm hoping kind of in the fall I'll be able to talk about that more freely. But this system also plays into sort of auto remediation. So if we have high confidence on what the root cause of the failure is, we know based on logging input, other data sources, we can choose maybe to roll back a deployment or change a configuration. Maybe you don't need to wake somebody up in the middle of the night to show them what the failure is. Maybe you can just fix it automatically. So this is kind of the world that you get into once you realize the power of this context that tracing represents. But so far, this is just context, and I'm just talking about failure systems. I said before that I'm embedded in the performance infrastructure team. So how do we use tracing for performance use cases? There's a whole lot here. So let's take a look at kind of our simplified version. And let's say that we had a mandate to take this API response time down from around 700 milliseconds. Let's say we wanted to get down to 500 milliseconds. Let's look at how we could do this here. Well, if we collapse some of these spans to make this a little bit easier to see. Okay, so it becomes pretty clear at this point, looking at this trace. This section over here looks to me, just the way that these line up, that this is probably a thread pool with 3 threads that are making these individual calls. When one of them finishes, it looks like we spawn out another one, and they seem to happen in batches of 3. So one thing that we could do here is maybe increase the number of calls we're making in parallel. Right? This would reduce kind of the series nature of these calls. That would get us maybe, I don't know, maybe 100 milliseconds speed up overall. But that doesn't really seem significant here. And what tracing is good at is showing us critical paths. So immediately, this 316 millisecond call seems like it's screaming for optimization, right? Let's take a look at what we have here. It looks like we just have thin proxies down to the database, and the database responds in 315 milliseconds. It's MySQL, I'm not that surprised. So why don't we do something, maybe we build a secondary index or something so that we don't have to incur as much latency here. There are various schemes for optimizing MySQL. So maybe this is our first targeted optimization, right? And if we can make a 50% improvement here, that basically hits us to our target that we were asked to increase performance to. What about this find nearest? Well, each one of these, as we looked before, has a driver ID. And it looks like some of these are different. Yeah, so if the request to get driver is requesting various different drivers, they probably don't need to happen in series. Why don't we take all of these calls and instead of calling out to get driver in series, why don't we just do this in parallel? And given that this is about 200 milliseconds, we'd now be bound by our longest call. It's like 40 milliseconds. So we could shave 160 milliseconds off just by transitioning from serial calls to parallel. Okay, so with all of this combined, we've like far exceeded the expectations for performance improvements. So Jaeger really makes it easy to understand critical paths and to make targeted optimizations. But I made a little bit of a logical fallacy here. I'm not sure if anyone caught that. I sort of made the assumption that the database always responds this slowly. What we're looking at right now is just a single trace out of many, many traces, right? There are many requests flowing through the system. Maybe MySQL is just having a bad time. So what we need is a mechanism by which we can look at these aggregated traces and understand performance holistically, not just in a single example. It's really useful for a single example when you're searching for a particular performance problem. When you're looking at efficiency and performance for the entire microservice architecture, you really want to move towards aggregation. So early on when we were trying to use the tracing data set for performance, we were looking at these efficiency problems. We were aggregating traces. We were understanding what is the most expensive for Uber, what are the critical paths that we should optimize at large. And we realized pretty quickly that this isn't just, that we were kind of taking it too far. That engineers were just having basic problems that tracing could solve right off the bat. And so we started to build tooling to expose some of these answers to engineers directly. And what we came up with are basically two tools that are now being incorporated in Jaeger. I'm going to showcase kind of my demo internal versions. I'm not a front-end developer. I do not think that these tools work fantastically, but they are making substantial impact at Uber right now. So the first one here is the dependency graphs. Okay, so this is an actual dependency graph of a service at Uber. It has basically been obfuscated with animal names, and endpoints have been replaced with verbs. But what we have here is kind of a mid-level service. We have a handful of consumers. We have a handful of dependencies. But this gives us a great understanding of who relies on us and who we rely on to get work done. This is something that, in the complexity of this picture, is not immediately obvious, right? And like I was saying before, this is just one particular example. You want to know who all of your potential consumers are, who all of your potential dependencies are. So this tool is really useful for that. One thing I'd like to point out is that it kind of makes it seem as if every path is possible through aggregation. So we need a way of getting back down to single instances. And we do this through the path filter. So this is our focus service. And what I'm going to now do is filter for paths that include this focal service and some upstream or downstream. So just looking at this, okay, bonobo to eel looks interesting. And so these are now the paths that flow from bonobo to eel, don't know how to pronounce that, to hare to echidna. These are just service connections though. This still isn't showing us the full trace context of endpoints. So we have the ability to change how we are viewing this. Cool. Okay, so now we can see that bonobo earn calls into eel satirized, balaness rain. There are a few calls here. We don't really have an understanding of ordering. This is still just dependencies. And finally, it ends up at echidna cast. So we could probably say echidna cast is a database. Maybe we're interested in how balaness interacts with this database in some way. So we can filter this by cast now. We can see, oh, okay, actually, echidna cast isn't a database. It just seems like in that previous call through eel, it stopped at echidna. Well, that kind of implies the service has some element of caching, and it didn't need to read through to that database to get there. It looks like this hurry endpoint is maybe like an internal gateway for like, which is probably some kind of store operation. So this is kind of difficult without domain knowledge of what these services mean with it obfuscated like this, but for an engineer who understands kind of their place in the larger ecosystem and is deciding to make a migration, deciding to make a change, trying to figure out why their service is suddenly failing. Is it one of my downstreams? How are those services doing? This kind of holistic context of this dependency graph is extremely useful. So I've talked a lot about context, and really what we're looking at so far here is structure. Structure actually is pretty useful for a lot of problems. We kind of assume that this is a database, that this like endpoint is some kind of store operation. Maybe this endpoint is storing customer-sensitive information in a database. Well, from a security perspective, I really care about what top-level endpoints I can use to reach this sensitive customer information. So now, instead of having to monitor absolutely every endpoint that's exposed through a gateway, maybe I can look at the set of databases we've identified as being sensitive and understand what possible entryways there are to abuse to reach these databases. So that just reduces the scope of this security problem. If we are talking about change management, 80% of outages at Uber are caused by changes. That's mostly because people don't know who is dependent on them and what the full implication of these changes might be. So it's really easy now with this dependency graph. Let's say you're deprecating a service. You talk to all of your upstream callers over email, or your manager does, and they say, yeah, we're good to go. Everything's totally migrated off. Well, you can pull up this dependency graph and see, do I actually still have one-off endpoints that I wasn't really expecting that are still calling into my service? If you deprecate your service, those endpoints are going to start failing. That's now an issue for you. That could potentially be an outage. It could potentially have customer impact. It's really difficult to know without the full context here of this structure. Just having knowledge of your service in general is really helpful for new development. And especially in an outage scenario, you might know that your service is failing. You might know that your downstream service is failing, but you don't know what happens under the hood, underneath that downstream service. And you don't really know what the root cause is without the ability to combine alerting with these dependency graphs. Okay, so this is all still just kind of structural. But when we were looking at tracing, there were errors tagged, there were logs, and there were latency metrics. So even though we're just viewing the structure of aggregated traces right now, this is actually a much richer data set than what this visualization shows. So this is exposed through an API. Any engineer can pull the full dependency diagram down. This is just one service's perspective. If you want to understand kind of how large the big picture is, this is a gateway for maybe like a quarter of endpoints that are served for a particular customer use case. This is with the collapsed service view. If the demo gods abide, I can show you. Yeah, this is the complexity of like a single gateway service. One of many, and one of many endpoints. So this tool is not even built to handle graphs of this size. This is really like unimaginable complexity. This is what it takes just to serve trips all the time. This is the kind of mental model people who are dealing with outages have to have. Like I said, these are all being incorporated into Jaeger. This is getting totally revamped, so it'll handle graphs of any size, no problem. Okay, so through aggregation, we're able to understand more about these services, not about particular instances of traces, but about a holistic picture. We've decorated this structural graph with a lot of metrics, and one of the most useful we've found is latency measurements. So what we have here is essentially a histogram of latency calls to the same service that we were viewing earlier. I'll point out that this is a modified log scale on the x-axis and a log scale on the y-axis. So basically our latencies typically fall between 500 microseconds and 15 seconds. So this graph is built specifically to showcase our latencies. When I started building this and I looked at these graphs, immediately what jumped out to me is that it seems like they're very multimodal. Just looking at this, it looks like there's kind of two modes from here to here and from here to here. So the first question that jumps to mind is like, is this an intrinsic workload, or is this some element of who's calling into me? So like, is it the same callers who are passing me like variable data size that just takes a lot longer to process, or are certain callers more intensive than others just by nature of their requests? So what this visualization allows you to do is decompose these latencies and understand what endpoints they're calling and who your upstream callers are. So that's what this brush selection is doing. You can see that we have estimated call counts by upstream and endpoint. All these numbers are fuzzed, but basically it gives you a rough understanding of who the major contributors to this latency band are. So if I drag this around, you can see on the right side, like cow bring seems to be pretty common. The rain endpoint seems to be most common across the board. So why don't we go ahead and just filter by rain? Okay, didn't really make a big change. So that to me as a performance engineer is concerning. What that means is that this single endpoint is multiplexing a ton of responsibilities. So maybe this makes sense to break into different services. Maybe there are targeted optimizations we can make. Maybe our upstreams shouldn't really be calling this service. Maybe there's a better way to do it. So again, looking through, we have like cow, bring. Oh, that's interesting. So like right here, parrot, sprout pops up, right? It's like the second biggest contributor here, whereas it drops pretty quickly as you fall off. So let's filter by parrot, sprout. Okay, yeah, so parrot, sprout falls entirely in this region. And it does have a pretty significant long tail. Remember that this is a modified log scale. So any sort of long tail that you see here is actually like more exacerbated in reality than what we're seeing through this visualization. Same is true of multimodality. So this tells us that like something about parrot sprout when it calls into this rain endpoint has different performance characteristics than what we were seeing at the low end of the spectrum, right? So if we turn our filter off again, we can kind of grab through this area and we see we have cow bring. So let's try that. Okay, cool. So cow bring seems to really have a pretty fast latency, but then a huge long tail. If you cared about optimizing this rain endpoint in general, maybe you'd focus on what parrot sprout is doing to have a latency band kind of in the upper region versus what cow bring is doing, which seems to probably be more of like an intrinsic workload problem. Maybe you could even look at one hop above cow bring and see if there's some element of intrinsic workload that propagates through there. I'd also like to say if anyone has questions, just heckle me. I don't care. That's fine. I'd love to answer questions in real time because I'm going to go through a lot of different things. So yeah, great. So what we looked at here was kind of like decomposition of latencies according to endpoints, according to upstreams, according to downstreams. Not in this visualization, but we can also do that. And we saw that kind of looking at which upstreams gave us a lot more information about how our endpoints were processing. So that led me to start thinking about these gateway services that, remember, have this kind of complexity. These are usually like heavily staffed teams with really smart engineers who are focused on performance all the time. But I figured that there were probably teams that were understaffed, multiple hops away, who were contributing to these latencies and were magnified up the stack, right? So now we have the ability to view latencies in the context of a graph structure and understand kind of how workload flows through the system and how that impacts latency. So with these graphs, this is now not the same graph we were looking at, this is the gateway graph. What we can do here is sort of a latency decomposition. If we want to make this particular gateway endpoint faster, we need to figure out what its major contributors are as we move down the stack. Because looking at the complexity of this graph, the difference between 5 and 10 milliseconds at the bottom might correspond to timeouts as they're magnified up the stack, right? If you have repeated calls of 5 milliseconds, that might add up to much more than repeated calls of 10 milliseconds. Some service might time out. Now you have a top-level retry, which is just a waste of resources. These things really have like huge cascading effects that are difficult to understate. So what we were able to do is basically looking at top-level endpoints with a focus on optimization, particularly for latency, decompose latencies as we move down the graph structure, and identify the largest contributors to those top-level latencies. What we found through this process is that P95s and P99s don't matter as much as variance. So we're calling this variance decomposition. And it makes sense, right? If there's a large amount of variance very low in the stack, that's just going to get amplified as you move up the stack. And so by identifying services that might have a quick response, but have a large variance, you can actually see the impact on the top level. And by reducing the latency in this variance response, I mean, this is a huge band of latency response, right? From sub 1 millisecond to almost 10 seconds. By tightening the latency response here, by reducing the variance, we're also causing a reduction in P95s and P99s, just intrinsically. Okay, so we talked a little bit about what this decorated graph is good for, kind of identifying intrinsic workloads, identifying multiplexing of responsibilities over endpoints. We talked about variance decomposition. So if you combine this graph structure, these latency responses, you can do a lot of cool things. One of which is kind of moving strongly connected services around data centers. So there's a variety of business use cases for this, but you may need to basically just offload work from one data center to another. Maybe you are starting to move into a new data center and you need to be shifting services over. Maybe you're destroying a data center and you need to remove them in like a responsible ordered fashion. The latency histograms here in combination with the dependency graphs give you the ability to understand strongly connected services that can tolerate additional latencies between data centers. It really makes you understand the repercussions of this kind of move instead of just doing it experimentally, watching your systems fail, reverting it, trying it again in a new way. You can really predict out front what kind of impact these might have. Okay, so while I've been brush selecting here, you may have noticed this little box about representative Jaeger traces, and it says 0 traces found. That's because this is a demo data set. We talked about moving from a single example to understanding that example in the context of the big picture, especially in terms of latency response here at MySQL. You know, is this representative of the larger whole? You might want to do that process in reverse. So when you're looking at these kind of like multimodal latencies, understanding intrinsic workload, you want to get back to example traces that cause this aggregation in statistics, right? You want to find, in this particular latency band, show me some traces that occurred here, right? I want to see all traces between 2 seconds and 7 seconds because these are causing timeouts, they're causing errors, they're causing customer impact. That's what this button allows you to do. It allows you to jump out to representative traces according to your filter criteria here. And I found this to be a really powerful tool. If you think about the standard debugging process for like a single piece of code running on a single machine, you kind of take for granted that when things catastrophically implode, you get a stack trace, right? The stack trace is essentially the same reconstruction that we're doing here with distributed tracing. Imagine trying to debug a code problem where all you know is the particular function that failed, and you have no idea why. You have no idea who's calling into it. You have no idea the context of it. This is the world that many people are living in with microservices right now. So while tracing solves this reconstruction problem, what I want to show here is that it also solves kind of this reproduction problem. So a lot of times when you find a bug, you want to be able to reproduce it, right? That's not always possible when you have this large-scale distributed system, especially if it's a problem that's only occurring in production data. You're not really sure why. It's much easier to work backwards from here's an occurrence of that problem, let me go take a look, than trying to reproduce it from the bottom up. So by brush selecting in a particular region, we get traces that are representative of a particular problem space that we might be investigating. So I want to kind of end with an example in this space. I think this is probably one of the coolest performance examples I've seen. Who here writes in Go? Just by show of hands. Okay, Wow. Of those people, how many have used GoTool pprof? And okay, you're the only one. Have you also used GoTool trace? Cool. Okay, we've got one person. So I'm going to get into like kind of some Go specifics here. I think it is probably transferable to any other language, and I'm going to try and explain it as we go. Okay, so as kind of frequently happens, we had an engineer drop by our chat room, and as is almost always the case, they said, hey, I have this problem, and I'm not the problem, it's the person I'm calling into. In some sense, you can consider Jaeger to stop finger pointing, or on the flip side, you could consider it finger pointing as a service. This engineer said that basically he was experiencing timeouts in 0.001% of all requests. I personally have never had to debug a problem that occurred with an incident rate of 0.001%. But due to our scale, due to the volume of requests he was receiving, this is actually a substantial percentage of timeouts. And leading up to one of our peak business days, he wanted to ensure that this timeout wouldn't happen. For some context in his service, it was written in Go, and essentially it was an optimization step in the rider and driver pairing. So if it timed out, we just wouldn't retry. It wasn't that important of an optimization step. But he was starting to think that it could have bigger impact than we suspected. So he really wanted to fix this leading up to this high volume day. So he came to us and he said, yeah, here's the deal. I have this service. It's barely ever timing out. When it does, like, I'm so sure it's the database. So can you guys give me some traces to show me it's the database so it's not my problem anymore, and the database folks can figure it out. So what we did was we used these latency histograms. We jumped into his service and we selected the long tail, jumped out to traces, and I don't have the traces here, but essentially what we found were, this is like his service here. It would respond in like 120 milliseconds, and the database would respond in like 2 milliseconds. So I started asking about what his service really did, and essentially it just kind of like looked at the response of the database and repackaged it and just sent it back up the stack. So why is it just hanging out for 100 milliseconds? This was a pretty strange problem. So immediately we started nerd sniping everyone around us, and they started coming over, and we looked at some code, and we're like, yeah, there's really nothing here. What could possibly be happening? So the engineers set up a kind of local test bed, started shadowing traffic from production, really went to heroic lengths here, and sorry, let me back up. So we talked about GoTool pprof. That's basically a way of seeing like heap space and CPU. When you're looking at a performance problem that occurs in 0.001% of the cases, that's insignificant to the rest of the aggregated data, right? So those typical tools are not a way of getting to the answer here. So what you have to use is GoTool trace, which is basically emitting runtime statistics for every event that happens in the runtime. This is an extremely rich data set. Our performance engineers are actually looking at how tracing and GoTool trace data sets are kind of intrinsically related. So there are kind of analysis tools that we want to work holistically on both of them, but for the case of this example here, let's go ahead and look at that trace data. Okay, so keep in mind this is every single event that is happening in the Go runtime. I don't want to get into too many Go specifics here, especially around the thread model, but I'll just point out that we have this notion of Go routines, which are extremely lightweight threads, to the point of being able to scale up to potentially millions of Go routines. We have heap stats on the top, and you can see that basically these are increasing monotonically until there's a garbage collection event right here. This layer is networking events. We have syscalls, some timers, and then the really like dense area here. This is actually Go routines running. This is what functions they're running at any particular time. So basically what he's doing here is simulating a load test for his service. And you can see that basically we have some sort of networking event, We have a spike in Go routines. This is really typical for a Go service because Go routines are so cheap. You get a request, you spin up a Go routine that will sustain itself for the life of the request. So we have a little bump in Go routines. We do some processing work, and then there's a gap. There's also networking events here. This is his service calling out to the database. We can see that the database is responding pretty quickly, right? That's like 2 milliseconds. Then his service packages things up and sends it back out to whoever the caller is, right? And we can see this pattern happen over and over and over and over and over again during his load test. So we got to start looking for the timeout events here. And with the Go tracing data, this is actually really, really easy. So what is happening here? His service is just stopping processing. There's just these long gaps of silence, right? Engineers' favorite response to this is like, oh, it must be garbage collection. Like, oh, your service can't do anything, it's getting garbage collected. Actually, does anyone want to shout out kind of what they think the problem is here? Edge work? Network problems. Okay. Network effects, what did you say? Same thing, network effects, okay. I'll also point out that we're running on shared platform with this service. So this service can potentially be throttled in some way. So that was actually the kind of major theory in the performance team, was that this service is actually getting throttled on the shared platform, and so it's not able to run. It's not that it doesn't have work to do, it's not able to run. So let's talk about garbage collection, throttling, and networking effects. Those were the 3 theories here. So first, let's go check out a garbage collection event. So to be fair, like, garbage collection is almost never the problem with Golang. I've seen some minor issues with fragmentation, but GC pauses are like very, very minimal. So you almost never have performance impact here. And in fact, we can see that in this case, the GC pause was like 8 milliseconds, which is kind of significant. Can you shout it? Right, yeah, so this is what I was talking about with like shared platform or CPU throttling in some way, right? So this like, we were just kind of getting going with shared platform. We weren't really sure like what the edge bugs might be. So this was a really prominent theory at the time. But we actually have a smoking gun here to disprove that. So if we look at these like periods of silence and we zoom in, we can see that we actually do have some Go routines run. Very infrequently, but this means that the runtime had to have been scheduled. So it's not that the process isn't able to run, it's truly that the process is sitting there saying, I have no work to do, right? We have these stats emissions, so it's not CPU throttling. We looked at garbage collection. So what we're left with is networking, right? At Uber, we run software networking. So this is really useful for routing. It's really useful for circuit breaking, right? You don't want cascading failures in a system that's as complex as what I just showcased. And what's even spookier here is that the start to finish gaps on these silent periods are 100 milliseconds. Okay, no performance problem happens exactly 100 milliseconds. And even more than that, the start to finish here is 0.66 seconds. Okay, those two things are way too round. There's some human interaction here that's causing this problem. And this is just a 12-second trace, but he took traces for like 30 minutes, right? And what we noticed when we were looking for instances of this problem is that it reoccurred every 2 minutes. So we have this really regular interference. It turns out that it was a bug in our software networking. I think it had to do with advertising events where we would actually block incoming network requests. So his service was truly just sitting there with nothing to do because the network was blocked by some advertising event on an incoming stream of requests, right? This problem would have never been noticed if his service wasn't important to customer satisfaction and trip optimization, it would have never been noticed if he didn't have the volume of requests that made 0.001% significant. We never would have been able to get to it if we didn't have the ability to jump from latency histograms to those tail latencies. He would still be sitting there blaming the database team. Without the richness of the Go tracing data set, we wouldn't have been able to identify that this wasn't CPU throttling from shared platform. And we certainly would have never discovered this software networking issue, which actually was deployed to like a large number of services. I think that just really showcases how tracing is like one element in a larger plethora of tools that we use to diagnose performance. And it also shows how interesting some of these performance cases are when you have extremely complex systems running at a massive, massive scale. So if you think these kinds of problems are interesting, then you should come work for us. We are hiring both for the testing team that I had talked about, for the Jaeger team directly, for my performance team, for tool teams that use these tracing data sets, either for performance or anything else. If you want to get in touch with me, I don't really do social media. You can tweet at UberEng. You can email me directly, bwestlin@uber.com. That is my LinkedIn. You can send me a LinkedIn message. Please say that it's like related to this talk, or I'll probably ignore you. And thank you all for listening to me. It's a pleasure to be here.
Alguém quer perguntar alguma coisa? Temos tempo para uma ou duas perguntas.
So I think for Q&A, it's better if just like whoever's interested wants to kind of gather around here and I can answer questions more personally.
We have time for one or two questions.
One or two? Okay, yeah.
Yeah. Hi, good afternoon. I want to ask how expensive is for the applications to log all that information?
To attach all those logs to tracing data?
Yeah, because they are logging a lot of information. How
yeah, so
expensive is that?
these systems are probably already emitting those logs. The tracing doesn't really have a noticeable impact to performance. I don't actually have benchmarks on the additional context of adding logs, but we do a lot more than just these simplified logs in Uber. We have a lot of baggage propagation for a variety of things. I don't really know how much I can talk about baggage propagation, but I would consider it to be negligible, especially in the context of a service who has to wait on downstream callers or who isn't serving high volume. The more expensive part is the collection of logs than the emission of logs, because they can be quite large. I mean, so for the testing example, every one of those traces is annotated with the full testing log, which is quite long. Thousands and thousands of lines of text that's just simply attached as baggage. So I would say that we don't think about it. It doesn't make an impact, yeah.
Hi, congratulations for the presentation. I have kind of one or two questions. Okay, just around like, when Uber started to using like the tracing system, was there some people like resistance about it? Like they have like some other tools that have some similar like use case, and also like like with these questions, was like some kind of one big group or like one or two enthusiasts that start to create this new tool, like they didn't want to use Zipkin and so on?
Yeah, so our edge services, again, that's kind of what I was showing off here. This system is so complex that they had already built their own tracing system essentially, and it was done through like semantically tagged logs that were collected in their own way and pieced back together. Essentially the problem that I started with not wanting to solve for a distributed database, they solved themselves. So luckily when it came time to incorporate tracing, they already had like an interface that interacted with this logging tracing system that they had built. So it was just a matter of like wrapping Jaeger's APIs with what they were already calling. You know, maybe a little bit of semantic variance, but like pretty much one-to-one mapping between what they had and what we needed it to be. And in terms of resistance, we haven't really faced resistance. It's been more so, like, look at how many services are here. They all need to be instrumented in order for kind of this holistic analysis to work. That is kind of the biggest barrier to entry. So for Python, you can monkey patch calls, so you get tracing for free. We are trying to build high leverage solutions within Uber, so we have for Go a service that scaffolds new services. You get tracing for free if you use our dependency injection through this scaffolding. Java, I think, is also simple, but I don't know a whole lot about Java. We have node tracing, and we recently released C++ tracing as well. So some of those are more difficult than others. Usually the more higher leverage use cases have kind of director level mandate to get traced first. We have fairly good coverage right now, enough that we can do visualizations like this and make significant performance changes. Cool. If anyone else has questions, like, I'll hang out, you can come hassle me or whatever. Thank you.